So today we are going to talk about shelf life modeling of packaged foods. Have you studied shelf life modeling before in your packaging course? No, they don't cover. Can you think of it, what this topic would entail? Can you think what we could be talking in this topic, shelf life? Do you know what is shelf life? What is it? Yes? Keep the food in fresh condition. Anybody else? No? You don't know what shelf life means? Okay, so that's what we're going to learn in this topic. Okay, so it says matching the packaging to desired shelf life is necessary for quality assurance. So when you process the product, right, do any pasteurization or sterilization, baking, drying, any process you do, right, you prepare the food, you expect it to last for a certain period of time, right? In some product you want it to last for a couple of days, or a couple of weeks, sometimes months, and sometimes years, right? If you do not choose appropriate packaging, then you could lose the quality of that product very soon. For example, if you have coffee powder or milk powder, right? How long we can keep? Several months, right? But you just keep it in open cup or open plate. How long you think it was going to last? Within few days it's going to get spoiled. And how we can protect that? How we can extend it to 1 year? Appropriate packaging. Okay, and the time of that keeping quality, the time, that's what we are talking, the shelf life, that you can keep the product for expected quality time. Okay, so for that packaging is necessary. And in terms of the food processors, they have a legal responsibility to ensure shelf life on the package labels and that are accurate. So when you buy any packaged food, right, you must see some sort of a date on that. What kind of a date you'd see there? Expiry date, right? What does the expiry date means? That product is going to be good before that date. Our product is going to be good up to that date, right? So that's the shelf life, right? They specify based on how long is going to keep it with the quality which is acceptable to consumer. And that is a legal requirement, because if they do not write on the package, you would never know whether this product is good or not, right? So that's why food processor has to put that date. So by definition, shelf life means it's a period of time from the production or packaging, because packaging happens immediately after production, so that comes together, to the point at which product first becomes unacceptable under defined environmental condition. Okay, so whatever shelf life we define or specify on the package, it is under certain storage condition. For example, when you buy a milk, what kind of a shelf life you see on the milk? When you buy pasteurized milk, 2 days, that 2 days is at what temperature? 4 degrees C. If you keep it outside at room temperature, it's going to last just a few hours, right? So that's what it says, define environmental condition. So whatever you are specifying on that package, expiry date, it is based on under certain storage condition. So continuing with the definition, some say that it is period of time during which a food retains acceptable characteristics in terms of flavor, color, texture, nutritional value, again under defined environmental condition. When we buy the nutraceutical, you have some powders which are rich in nutrient, right? Could be vitamins or minerals, right? Those products also have some shelf life is specified or expiry date is specified on that package. Do you know what would be the criteria to specify that? Do you ever buy any powder? I think it's Boost or some of these powders which are rich in nutrients like vitamins and minerals. People have deficiency, or those athletes, they want additional nutrient, so they have these powders. Can you think what would be the reason or criteria to specify shelf life or expiry date on those products? It is not the taste or flavor, it would be the nutrient value. If on that package you're saying that one serving of that powder is going to provide you 500 milligrams of vitamin C, it means it should provide you 500 milligrams of vitamin C. Maybe after 6 months it's not providing you 500, now it's providing you 450. But on the label it says 500, it means its life is gone, because your shelf life is based on nutrient value. For milk, the shelf life is based on microbial count, because after 2 days you will have significant microbial count in there, and that would be spoiling the milk. Even you may not be able to sense it, but there is enough bacteria which are spoiling the food or your milk. Okay, so depending upon whatever the primary attribute for that product for which consumer is buying, that's one you look as a quality factor for specifying the shelf life. Another definition for shelf life is the time during which a product may reasonably be expected to meet its label claim for a specific attribute, such as vitamin supplementation. So that's what example I gave you. So on a package, which one of this label you see when you buy the product here? Use by date, expiration date. So do you see all 4 of them or some of them? So sell by date is not usual here. Some places it is. Use by date, do you see? Best before or expiry date. Out of 4, which one you think is you would feel is most appropriate? So if it says best before that date, after that date, what does it mean? So you're going to eat it or not? And how would you decide to eat or not?
There might be some decrease in its quality.
And what is that quality? For example, milk, if it says 2 days, you wake up in the morning, say, oh, the date was till last night in the morning, and would you drink that milk? So for the product for which shelf life is based on microbiology, you don't want to, right? Well, strictly technically speaking, when it says expiry date, you just throw it. Doesn't matter what it is. But as a food scientist or food engineers, you can at least guess or do some judgment, is that if the quality deterioration is because of physical attributes. For example, its crispiness is gone, right? People like chips because it gives you crispy texture, right? So let's say if it is exposed to some relative humidity for whatever reason, it's not crispy anymore. So you could still eat, it's not going to taste good, but if you're hungry, you don't have anything around, you really want to eat something, well, even you may not enjoy eating that, but it's going to give you some calories. right? But as I said, if it was a high moisture product, their shelf life is based on microbial or microbiological quality, not the physical quality, then you don't want to attempt, right? Because if you do, you could get sick. Okay, so people consider that the expiration date or expiry date is the most appropriate and very clear. That expired means it's expired. For example, if it's used by that date or sale by that date, of course, grocery store is going to sell by that date, but what does it mean for consumer? Shall I eat it or not? The grocery has sold you that product, but then you are not sure whether you eat it or not. So sometimes food companies put the labels for their benefit rather than making clear to the consumer. But there's no strict regulation in many places. So then food processor could put one of these labels on their package. So what factors affects the shelf life of the product? Can you think of what factors would affect? No, those are the, what would change the shelf life of the product? Environmental conditions, physical factors. Sorry? Yeah, atmosphere inside the package, correct. So environment outside, inside the package and outside the package. Type of packaging can influence the shelf life. Initial microbial load. So that's a part of the food. So food factors, environmental factors, and packaging factors. Yeah, so that's correct, but you could lump that into part of the environmental factors. So there are food factors. It means the inherent chemistry of the food. As you said, some product inherently have a higher microbial count compared to the other product. Then even if you expose to same environmental conditions, even if you use same packaging, their initial quality was different, then a shelf life would be different. Some product, they are inherently unstable, right? So then, no matter what packaging you use, what environmental condition you use, they're going to spoil very quickly, right? So let's say, do you buy milk bread, soft bread, right? What is the shelf life? 1 week. Anybody else? Let's say 3 to 5 days, right? Short shelf life. What kind of packaging we use? Plastic bag, right? You think if I use a glass or aluminum foil or metal cans, you think I can extend the shelf life? No, right? Yeah, you're correct. Because it's a high moisture product, it is not a sterilized product, right? Inherently, a lot of chemistry is going on, inherently very unstable because they're rich in a moisture. There's no preservative in it. So it's going to spoil. It's not spoiling because of the external factor, because of the internal factor itself, right? Of course, if you use very, very poor packaging, even you cannot have 3 days. It may spoil even 1 day. So some level of help is there from environmental factor, but probably not a lot. So food factor by itself influence the shelf life, environmental factor, as you all mentioned, and the packaging itself. So how do we do the testing? So we hold the product under set of appropriate condition. And what would be the appropriate conditions? Whatever is intended for, right? So for example, bread is supposed to be room temperature. Milk is supposed to be refrigeration temperature. And frozen fish or any frozen vegetable is supposed to be freezing temperature, like minus 18 degrees C. So you hold that product under that storage condition and then keep on monitoring the quality. Which quality you will monitor? Will you monitor all the qualities? Have you done any industrial internship? Have you worked few months in industry? No, don't go to in summer months to spend few months in food processing company or any company? It's not part of the BTech program, no? Yes? Okay, so can you now imagine if somebody is making biscuits, let's say Parle-G is making biscuits, and they want to figure out how long we can keep it, what would be the shelf life, what date they want to print on the package. Can you now think that if this responsibility is given to you, how would you decide what you will do? How will you proceed? Boss will say, hey, here are the biscuits, and we can package in different kind of a plastic packaging. So please suggest me, which packaging I should use and what the date we should put on it.
What you can do means with the packaging material we can find out what is water vapor transmission rate, and upon that we can check whether the biscuit is getting soggy after some time or not.
And how will you find it soggy? Sensory analysis. So in sensory analysis, you will be looking whether the biscuit is soggy or not. It has a crispy texture or not, right? Because people like biscuits for that texture, right? Probably not for the color, right? Probably not for its nutritive value. As long as it's a crispy, so that's the primary attribute, right? So for every product, people buy it because of one or two quality attributes. So that's what you will monitor. So you may select different packaging materials or, based on some calculation as you suggested, water vapor permeability or whatever, you have science behind it. You select few packaging, put your biscuits in it. It's supposed to be stored at room temperature. Store at room temperature. We normally know, let's say it lasts for 3 months or 6 months. Then you don't want to check every day because that will be too many of experiment. Maybe every week, every 10 days, you take it out, few people around who can try it, and if they say okay, then keep on doing, and one day they say no, it doesn't seem good, it's not having as crispiness as I would like to see. So before that, whatever experiment was done and it was accepted, that's your shelf life. So for that biscuit, for that particular product, you are using primary quality attribute is the crispiness. So when we say that you monitor the state of the product, state means that quality attribute for which people are going to buy, a consumer is going to buy, and you keep doing until the product fails. Another way saying that the time elapsed to failure is the shelf life of the product under those conditions. And food industry does very frequently, in fact, shelf life type of research is not done much in universities. It is mostly done in the companies. So food industry does to learn the effect of ingredient changes. So for example, they are preparing biscuits using some ingredient, right? And there may be 50 different ingredients. And then at some point they decided, they're not going to buy sugar from this company. There's another company, they are selling not the sugar made of sugar cane, but it's the corn-based sugar or beet-based sugar, right? There are different plants you can use to make sugars, right? They say, okay, if you are changing the sugar, what will happen to our product? Is it going to last the same time? If you don't know, let's do the shelf life to make sure that if you are putting label for the previous formulation for 6 months and for the new formulation, is it still going to be 6 months or not? Or manufacturing changes. Suppose they improve the technology of baking, they buy new ovens, they change the conveyor belts. Anything they change in manufacturing process, they say, well, we want to make sure it's not going to affect our product quality and shelf life. Different type of packaging materials, if they come up with an idea, say, hey, maybe let's do the flushing of the headspace. Rather than having oxygen, let's flush it with nitrogen. Well, if you do that, that's going to affect the shelf life. So any change they make, they need to evaluate the shelf life. Or even it says now distribution abuse. So they have distribution chain within the country or in the state, in the city, and now if some new system has emerged for the distribution, then again they want to make sure that it's going to last as it is written on the label. So overall, they would like to see a basic stability of that food product. Now, imagine that you work in a company, that company produces a product, and that product shelf life is generally 3 years, right? And then now they make some manufacturing changes, or they make some packaging changes, or they make some ingredient changes, and that brings a question, say, well, now we want to make sure that the shelf life is 3 years or not. So if they start doing experiment, because of this change in manufacturing or processing or packaging, that there is a possibility that the shelf life may be off by 1 or 2 months. It may be a couple of months better or a couple of months lower, right? How they will figure out? By doing the experiment for 3 years. You think company can afford to wait 3 years to learn that now the shelf life is off by 1 month? They cannot, right? So in order to get the quick results, engineers like you, technologists like you have come up with a method, what they call accelerated shelf life testing. In that testing method, you hold your product under set of more severe test condition. So if, let's say, particular product is being held, supposed to be held or kept or stored at 4 degrees C, you try to store it higher temperature, maybe 6 degree, 8 degree, or 10 degrees C. If relative humidity affects, then you try to hold at higher relative humidity. And then you do the shelf life calculation under severe condition, and then you predict it back to the original condition. So at severe condition, what will happen? The product is going to deteriorate faster, right? And you all know the mathematics of deterioration. You remember we did first order, zero order kinetics. That's what it is. You're looking at the concentration on your vertical axis. You were looking concentration of nutrient, you're looking concentration of microbes. On the x-axis, what? It was time, right? So imagine now if you look this shelf life at higher temperature, right? Then you plot your x-axis for the temperature, and y-axis would be your shelf life. Higher the temperature, lower will be the shelf life. Right? So you do experiment at 8, 10, 12 degrees C, and then predict what will happen at 4 degrees C. Right? By doing this, you can quickly get the results, because the product was supposed to be last, let's say, several months at 4 degrees C, then is going to last few days at higher temperature. So usually higher than normal temperature and relative humidity lower or higher, depending upon the product, is susceptible to higher relative humidity or lower relative humidity. And then data from this normal shelf life study on the same product is then combined with the accelerated data to figure out whether, what would be the effect of either manufacturing changes or packaging changes, whatever changes you are making in your process. Are you able to follow this? So typically they do, sorry?
So actually, in this you have mentioned that it is severe test conditions.
Mm-hmm.
Which are those test conditions?
Well, let's say temperature. Let's say frozen food. Do you know what is the shelf life of frozen food? Probably a year. I don't know how much is here, but let's say in the US it's 18 months. For most frozen fish or frozen meat, frozen vegetables, the shelf life is 18 months. right? Now, if they make some ingredient changes in their product or packaging changes in that product, and they want to figure out what would be the shelf life, is it exactly 18 months or 17 months or 19 months? Okay, so frozen storage is done at minus 18 degrees C, right? But if they conduct their experiment only at minus 18 degrees C, it's going to take them approximately 18 months to figure out, right? But then rather than doing experiment at minus 18 degrees C, they can do it minus 10, minus 8 and minus 6, right? So you know at higher temperature, it would not have the same shelf life, right? So you store it higher temperatures, probably within 3 months, 2 to 3 months, you would know what is the shelf life at those temperature. And then you can plot, right? On x-axis, it will be your temperature, and y-axis would be shelf life, right? So you would have the relationship, temperature versus shelf life, and then you can predict what will be the shelf life at minus 18 from that graph.
But in most of the studies, sir, for shelf life prediction, they use the storage condition as a storage environment. In few research papers, they are already mentioned as a different temperature and RH. But as far as considered accelerated storage condition, they are using 38 degrees C or 40 degrees Celsius temperature and 90% RH.
See, that's all depends upon the product you are looking at it. See, for example, if it is a frozen food product, you're not going to do 38 degrees C or 90% relative humidity. That what you are referring is the dry product. So dry product at room temperature would have certain shelf life, let's say tea powder or coffee or biscuits, right? We normally store it 25 degrees C. So if you want to do accelerated shelf life study for those products, then of course you will use 38 degrees C, 45 degrees C or 50 degrees C. Higher temperature than you normally store, right? But for frozen product, you're not going to store at room temperature or refrigeration temperature, because then they are not frozen anymore.
But in most of these papers,
Mm-hmm.
not told for frozen foods, but most of the papers, they use the same conditions, 38 and 90% RH. How come we can use that same temperature for all the products?
These all the product which you are referring, now you recall if you have read those papers, these all the product you are referring, they are dried product.
Most of the dry products, sir.
All of them, not most. Or you would have canned product, which are normally, so product which are normally stored at room temperature, you would store at higher temperature. Now, your question is genuine. You are saying 38 degrees C. You know why 38 degrees C?
So actually that particular combination, 38 and 90.
Yeah, 90% relative humidity is also used because in environment you have a lower relative humidity, and then you want to accelerate, so you will pick higher relative humidity, which
In most of the papers it is mentioned as if it is product can stable at this condition, 38 plus 90, it is considered as it will be stable for all conditions. It is considered as the most unfavorable condition for the food storage.
correct, but that testing is not for the accelerated shelf life testing. That testing is that normally we store at 25 degrees C, but in case of there is an abuse in terms of the storage condition, then it's going to deteriorate fast, and if the likelihood is very high that product may go through higher temperature, then what would be the shelf life? But that's not a really accelerated shelf life testing. This accelerated shelf life testing is a very controlled study. It's not to test at one temperature. It is to test at 3-4 temperatures, so that we can put the mathematical equation through these 3-4 data points, so that we can predict back the shelf life at room temperature or the normal storage condition temperature. What you are talking about, that is in case if there is a temperature abuse. So for example, milk, you are saying the shelf life at refrigeration temperature is 2 days. You know how they find out this 2 days? Actually, if you have pasteurized milk, for example, in US and Europe, you can keep that milk, pasteurized milk, for 21 days, not 2-3 days. Because if you really store all the time that milk at 4 degrees C, then it will have shelf life of 21 days, right? But that means that there's no temperature abuse. It means that this milk never experiences during storage more than 4 degrees C. So that's a truly, truly lab condition, right? But they know here, food companies, what is the temperature distribution, temperatures during distribution chain, right? They also know what is the temperatures in home refrigerators. So they did a survey, even in India, they put the thermometer, thermocouples or thermometer in the refrigerator. They found the normal temperature of those in fridges, home fridges or refrigerators is actually 8 degrees C. It is not 4 degrees C. We read this 4 degrees C in our textbook, when in reality and we do the lab experiment, it's 4 degrees C. But our home refrigerators are actually 7 to 8 degrees C. Some of the older one actually 10 degrees C, right? And then when, let's say, milk is pasteurized in Anand in very, ideal conditions, now they need to ship in different cities. How does this milk goes there? It's supposed to go in refrigerated trucks, right? But many times nearby distance, it is not the refrigerated trucks. Okay, even let's say if refrigerated trucks, which is maintained at 4 degrees C, when you do loading and unloading, that's under atmospheric conditions, right? Many times you would see the grocery stores, they're not keeping this milk inside the refrigerators because people will come in the morning, every morning, 8 o'clock or 7 o'clock, they would buy the milk. So they have a bucket, big basket, and then all plastic bags, they are sitting at the room temperature. Or even they're putting in a refrigerator, they are opening the door 100 times in a day. That is not maintaining 4 degrees C, even this is a very sophisticated refrigerator. So these are the temperature abuse for this product because they know, industry knows very well, these are the normal distribution or storage condition. It is not truly 4 degrees C. Because of that, they take account of all this and temperature abuse and they say, no, shelf life is not 21 days. It is actually 2 days or 3 days or 4 days. And so this is example for the refrigerated products. Same they do it for the dehydrated product, which are supposed to be stored at room temperature. So that again, if you look at the textbook, you will see room temperature is 25 degrees C. At least in US and Europe, they consider 22 degrees C. But if you look at the weather condition here, how many months or how many days in a year you will really have the 22 degrees C or 25 degrees C in the room where you are storing the product, right? Because many times it is higher when during transport from one location to another location, it is going in the trucks. Trucks is, going under the sun. You can imagine what kind of temperature product will experience. Because of this, they consider what you are saying. That's what it is there in the papers. That okay, let's try to store this product under extremely abusive condition, which is 38 degrees C, 90% relative humidity, and now let's see what kind of a shelf life it is giving.
And in most of the studies, they are predicting the shelf life based on only water vapor permeability of packaging material. They are fixing some initial moisture content of product being also, and they are fixing some critical moisture content. And they are just calculating the water based on the critical moisture content based on the water vapor permeability of packaging material. But is it possible to generate the degradation rate estimation, K value, under different packaging conditions at different storage conditions for different products? Is it possible?
Yeah, that's possible.
Sorry, in pouch.
Yeah, that's possible. And from there, you can predict which package is going to give you best shelf life. Again, that's the shelf life determination. But what we are here talking about is the accelerated shelf life testing. That whatever set of conditions you have the severe condition so that you have lower shelf life, and then predict back what would be the condition at the normal distribution.
Because presently only we are considering the moisture content. So that in that condition we can use both physical, chemical, maybe hygroscopicity, degree of catching, and microwave also. So that degradation, if it is possible, then we can directly predict the exact degradation in pouch.
That's correct. Yeah, you can do that. And also, as you are mentioning, your examples are mostly relevant to the dehydrated product. So that's where, higher relative humidity is relevant, because if they happen to absorb moisture, then its quality will change significantly, the physical, chemical, or microbial quality, right? But if it was a wet product, then probably relative humidity, higher relative humidity is a desirable, right, environment. So there you will not use, probably you will use lower relative humidity if it is in a polymeric packaging. And in case if they are in a glass containers and metal cans, then relative humidity really doesn't matter because there is no permeation of the gases or water vapor, right? Okay, so as we say that in accelerated shelf life testing, you store the product under more severe test conditions so that those severe test conditions give you lower shelf life so that you can finish the experiment quickly, and then using the mathematics, you predict back what will happen at normal storage condition, correct? What would be the drawback with this kind of accelerated shelf life testing?
Only one parameter is tested. The temperature is alone tested.
One parameter. What else?
So sometimes the mechanical damages, etc., damage during transport cannot be taken into consideration.
Then whatever is the shelf life of the product is there in general now, right? So that is based on temperature storage. But if the mechanical vibration which happens during distribution, then you should incorporate that in your shelf life study. So that's correct. In case of if you're just focusing on temperature, then you are considering only one parameter. What else? From the temperature perspective, let's say temperature was the only parameter affecting, not mechanical. Then also, just by increasing the temperature, if you are calculating back the shelf life at normal storage condition, with this idea, what would be the limitation or drawback? Let's forget about all other environmental stress factor, such as humidity, mechanical vibration.
Maybe the temperature which we are testing might not be the exposed temperature of that maximum exposed temperature.
Correct. Actually, what happens, many reactions could occur at high temperatures, which will actually never occur at low temperatures. So when you are designing the shelf life studies, whatever reaction you are monitoring, right, you will be monitoring one reaction or one quality parameter, right? So you are assuming in that accelerated shelf life testing, whatever your quality of interest, whether it's a color, texture, whatever is the primary quality attribute for your product, that would accelerate at higher temperature, right? We did study K, reaction rate kinetics, as a function of temperature. Higher the temperature, higher the reaction rate constant, right? So you are assuming that would accelerate the reaction rate, right? But there is a possibility that when you are using the higher temperature, of course that is going to accelerate, but then it's going to induce some new chemical reactions, which will never happen at those lower temperatures. And if those happens, then whatever prediction you are doing, that's not very accurate. Okay, so that's the limitation of this method, but there's no other way. So far we have found whether we could quickly decide what would be the shelf life if we do any manufacturing changes or any packaging changes. So it says minor changes can be studied using accelerated conditions, but it introduces new problems, new degradation reaction that do not occur or that may not occur under normal conditions. So these studies are often conducted to get more rapid results about the possible changes, right? So they are a bit crude kind of studies, but you can easily quickly get some idea. And of course, based on that, you design your shelf life, and then you label it, and it is going through the distribution change. If that prediction or labeling was not correct, you would have some feedback, from your suppliers through consumer, right? Consumer is going to complain to the grocery store. Somehow grocery store would complain from he or she they are buying, and then eventually industry would hear this feedback that, oh, we stamped the shelf life for 18 months, but actually product did spoil in 15 months rather than 18 months. Because whatever study they did in the lab, as it says, that they're not very, very accurate. Okay, so what are the mechanism of food deterioration from the shelf life determination point of view? So as you all mentioned, the loss of sensory qualities such as color, texture, flavor, nutrient, and so on. And this loss happens due to a variety of reactions. Some of this we listed in the very first lecture, that you could have post-harvest enzymatic reaction, microbial decay, and so on. There's a list, whole host of reactions that could happen. But from the, and it says that for most cases, we have not understood all the reactions very well. Some of them we only partially understood their chemistry. So when we are doing shelf life study, we actually do not really monitor each and every reaction, what is happening. What we monitor is actually one quality attribute for which, or maybe two quality attribute for which the product is sold, or consumer buys that product. So whatever the shelf life studies we do, these testing methods are very practical, and the studies are manageable. You can get useful results, and they are helpful in kind of a product development, not really to understand the complex chemistry happening in your food product. For example, you said that we will store the product and we monitor the sogginess in biscuit, right? Now, why the sogginess is happening, what the chemistry behind it, or what the physics behind it, you're not studying. Just you are saying you're testing every week, every 10 days, or every 15 days, you say it is soggy or not. Consumer is able to notice or not. So they are very simple studies, very manageable, very efficient in product development, but these studies are not designed to understand the chemistry happening in the food product. So that's what it is about the primary and secondary attributes, that we are not trying to understand what are the mechanism of degradation, right? We're just trying to understand the state where the product is going to be rejected by the consumer, depending upon its quality attribute. It could be primary attribute or maybe secondary attribute, right? So for example, when you go to the market, if you had to buy banana, how did you buy? How will you decide what banana you want to buy? Color, right? You're not tasting it for flavor, right? So color is the primary attribute. When you see the color is good, then what is the next thing you will do? Shape, firmness. So you would touch, even though color looks good, and when you touch and you press a little bit, right? And you say, my God, it's very soft. Ours very firm. It appears. They say, no, it's not ripened, even though color appears to be good. I like this color, but it's very firm or very soft. Then you say, no, that's not good, right? So this is how, it may still have the same level of potassium for which people claim, that it is highly nutritious, right? But you're not buying banana really for the potassium content, because you're not measuring that there, right? You're really buying for the color as well as texture. So it says, those attributes need not be saying that whether the product is inedible or not nutritious. It may still be very nutritious, but because it's soft and you don't like soft banana, then you're not going to buy it. So the way, companies does, they target the consumption group. It could be consumers, could be sensory analysts. Do you have sensory analyst jobs in food companies here? Okay, so that's one of the best jobs. You go everyday work, you have nothing else, but you will be presented variety of food, and you would say, no, I don't like this, right? And you go home. So that's your job. Or sometimes this testing is done by company people, or the people who are involved in a product development. So depending upon companies' interest sometimes. I have not seen here, but some places what they do, you develop this product, maybe sometimes a new product, you want to know whether people like it or not. Then you go to grocery store and give free samples. And then when you ask people, how does it taste? Do you like it? And based on their reaction, you kind of have a feedback whether people are liking this product or not. And many times if they really like it, they're going to pick up, they're going to buy that product. So that's kind of a feedback about the quality of your product. So practical shelf life or end of commercial life, need not worry about all degradation mechanisms. What we worry about that whether consumer is able to appreciate the quality of that product. That could be color, texture, or appearance. Now, if you see any product, they could have intrinsic stability or extrinsic stability. And intrinsic stability means that the internally driven degradation mechanism, which are part of the food component, right? The degradation is not being affected by the environmental factor, right? Because if you take away all the environmental factors, you take away the light, you take away the oxygen, you take away the relative humidity, like you just package in glass or metal cans in a dark condition, you store no light, no headspace oxygen, and then you see how long it's going to last. And that deterioration under those conditions is due to the internal chemistry of the food product. Okay? And the external factor or extrinsic stability is that its quality, a shelf life is being affected by the external factor or the environmental factor, and that could be oxygen, moisture, light, and so on. So if the product has very high rate of internally driven degradation, then it will have a short shelf life, right? As we were giving example for bread. Or if the fresh cut meat, if chicken is slaughtered today, even if you keep it refrigeration temperature, how long you can keep it? Not very long, right? Because it's rich in moisture, and probably during slaughtering, handling, there is a lot of microorganisms on the surface. The count will be very high because you have not done any processing, right? That product will have very, very short shelf life. And for that product, no matter how good packaging you use, it's not going to help, right? Because its internal chemistry, internal microbiology is responsible for the degradation, right? The packaging can only help if the food formulation allows a high rate of externally driven degradation. Is that food is being deteriorated because of the light, because of the presence of oxygen, or because of presence of water vapor, okay? Then packaging can help because packaging can protect from these external stresses or environmental conditions. So it is important for us, before we decide on packaging, whether high barrier packaging film or the packaging which can block the light is going to help or not, first we decide whether product is being spoiled by the external condition or by the internal conditions. Okay? So what they do to study the intrinsic stability of the food product, they make use of the very high barrier packaging so that you can avoid the effect of oxygen and water vapor. Then also you create a dark condition so you can avoid the effect of sunlight. What else? So basically oxygen, water vapor, and light, right? And in fact, you can flush, the oxygen from headspace, not only use the high barrier, but also flush the oxygen during packaging. So usually, this is what it says. It has a series of extremely high barrier packaging, as low as it is listed here, 0.005 ml oxygen per day, are very, very low water vapor permeability, and you flush the headspace with nitrogen. But in case if the product has an anaerobic degradation, then you can flush with the optimal gas mixture, because in normal condition you would have some level of oxygen, so you really do not want to flush the oxygen from there. So you want to maintain very optimal condition of the gas mixture there. So then these condition can give you, these testing can give you whether product is oxygen sensitive or the product is moisture sensitive, and whether it can take the, how it is affected by the oxygen concentration, right? Because you are going to remove all these factors. And then you do this testing, including the light, and then whatever shelf life it will give you, that will be the maximum possible shelf life, right? Because you are using the perfect packaging. Perfect package means you are avoiding the contact with oxygen, you are avoiding the moisture transfer, you are avoiding the light. When you avoid all these factors, whatever life you get, that is the best you can get, right? And once you know that this best is, if it is a couple of days, then probably you know that none of the packaging would matter, because the best packaging is giving you only 2 days or 3 days. So no other packaging can give you higher than that, right? But then if the best packaging is give you 3 years or 2 years, then you want to see, well, why I have to use the best packaging or the most expensive packaging? Let me see if I allow a little bit light, how much life is going to affect. Let me see if I had to have a packaging which has some level of oxygen transmission or water vapor transmission to see how much is going to affect shelf life, right? Because for each and every product, you cannot always use the most expensive packaging, right? Because if the less expensive packaging does not affect significantly, then you want to select that packaging, right? For example, if the product does not have lipids, does not have high level of nutrient which can be degraded by the oxygen, then probably you do not want to select high oxygen barrier, right? Because every quality factor of packaging is going to cost, right? Or if the product is not being affected by the environmental humidity, then that packaging need not have extremely high barrier to water vapor transmission. Because if you select that, of course it's going to help, but if you don't select that, it's also not affecting. And if it is not affecting, then why you want to select a packaging which has these features? Because any additional barrier feature of this packaging is going to cost the money. So for the shelf life testing, it is also important both ways, that you don't want to underestimate the shelf life, because if you underestimate, then you are going to select very excessive packaging, and if you select the excessive packaging, it's going to cost the money, right? But if you overestimate the shelf life, right, through your shelf life testing, then you are going to under-engineer your packaging, and then your product may fail. So you really want to have the optimal packaging. Does it make sense? If you don't have optimal packaging, as I said, if you overestimate, that product is going to be needing not very good packaging, and then if you don't use good packaging, then it's going to be unstable, it's going to fail. But if the package, this particular product does not need very good packaging, but if you do provide very good packaging, then you are going to spend extra money for that, right, which is not needed, because companies are looking for the profit as well. Does it make sense? So from packaging perspective, it is always important that you should have the perfect or right packaging or optimal packaging. Not excessive packaging, because you want to avoid the excessive cost, but not the poor packaging, because then it's going to suffer the quality and shelf life. And these are some of the abusive conditions, as you were mentioning, one of the students was mentioning that these abusive parameter could be temperatures, it could be humidity, sometimes it could be temperature cycling. Rather than having just higher temperature, you can have temperature cycling, because many times, especially for the frozen and refrigerated products, when you have the distribution, it is the temperature cycling, it is not the always higher temperature, right? It goes high temperature, then again comes down, then again temperature increase, then come down, right? Depending upon how the product is being handled. And then pressure abuse, manufacturing abuse, or distribution. For example, it could be mechanical vibration during distribution, or it could be light. So all these abusive parameters are there to study how the shelf life is affected by those parameters. This brings it again, the same equations that we have been seeing for microbial inactivation. We saw the same equations for chemical kinetics, for nutrient destructions and so on. For the shelf life also, you can use the same equation. So for example, this is a general equations, and if it is the zero order, then this is the form, and then you can break it down to this. In this equation, that you have concentration of the component at two different times. This is the initial concentration, this is the concentration after time t, and this k is the reaction rate constant. So in this case, you can use this same formula rather than this time t to monitor concentration, but this in place of this concentration of your component, you can put any quality parameter. For example, this A0. So in place of this concentration of the component of the food product, it could be the nutrient content. So if your shelf life is based on the nutrient content, for example, A0 initially is 100 milligram, right? And on the label, you are writing that your vitamin C content is 80 milligram, right? Even though starting is 100 milligram, because you want to sell, because you know during storage it's going to come down, and then you want to specify shelf life that as long as this 80 milligram is there per serving, it has a good shelf life. And then you study the degradation of vitamin C in your product and see how long it takes to bring from 100 milligram to 80 milligram, and that will be your shelf life. If you are looking for the crispness, then you measure that crispness using texture analyzer. So you are going to measure the force required to break your crackers or your biscuits, and then how this force is changing, and when the force comes to close to when consumer feels the product is soggy. So that's be your final value of your crispness or force, and then how long it takes to change that texture from initial texture to the final texture, and that would be your shelf life. So the same equation which we studied, we use for the microbial destruction or change in the chemical quality, you can use it for the sensory quality as well. If the reaction is not zero order, if it is a first order, again you can use the same equation. Yeah, you can use the first order kinetics to find out again what would be the shelf life by changing that concentration of that component or the sensory value for that component in that your product. Okay, so it could be springiness, chewiness, or texture, nutrient, flavor, color, whatever quality parameter you are measuring, what is the initial time and a time at which the color change is sufficient to give you the rejection by the consumer, so then you can calculate this your shelf life. Okay, so depending upon the order it is following in terms of the degradation, you can use the appropriate equation and then you can find the shelf life. Of course, if you have the effect of temperature on the shelf life, you can make use of the Arrhenius concept, or you can make use of the, this is I think for the Arrhenius, but I think I should have for the Q10 as well. And both concept what we use for the other chemical changes, you can use it for the sensory changes as well, or the shelf life as well. So here this table is showing you, for example, if your Q10 is 2, it means for every change, 10-degree change in the temperature, your shelf life is affected by 2 times. So at 45, the shelf life is 2 weeks, then at 35, it will be 4 weeks, at 25, it will be 8 weeks, and 15, it will be 16 weeks. But if Q10 is 3, then shelf life is affected by 3 times, and if Q10 is 5, then it's affected by the factor of 5. So this is how you can make use of these mathematics to calculate the shelf life at a given temperature, but then also you can calculate the shelf life at different temperatures.
But can we calculate it based on this K value, that reaction constant?
Cal-
D value and the T half value based on the K value. Can we calculate in cell pack also?
Yeah, so
Based on particular
first the experiment would be that you monitor any quality attribute as a function of time,
Yes, sir.
right? And then you can also monitor that quality attribute at different temperatures, right? As a function of time. So you do the experiment at, let's say, 15 degrees C, you do the experiment at 25 degrees C, and you do the experiment at 35 degrees C, right? And from these three different set of experiment, you can get D value or you can get K value.
But the D value, T half value or K value is different for the different temperatures.
Correct. So this is the effect of temperature, and that you can monitor either using Q10 or the Arrhenius concept, right? So you would know the K value and EA value, or you can find the Q10 value from K values, yeah, and then you can predict it back at any temperature. Okay, so this is what I have on this topic. If you have any question now for this.
How do we make sure that this chemical degradation or nutrient degradation follows the same rate of reaction like first order or zero order in the whole temperature range? Like it may be possible that from suppose 20 to 30 degrees Celsius it's following zero order reaction, and after 30 to 40 it may follow first order reaction. There are possibilities.
That's correct. So what normally you would do technically to make it sound, you will not predict beyond what you have done the experiment. So if you have done experiment between 25 and 35, maybe few degrees you can predict, but you are not going to predict at 65 or 75 if you have done experiment up to 35. You're right that it may not follow the same order of reaction beyond the experiment you have done. So whatever temperature range experiment you have done, within that temperature range you can predict, but beyond that is always, there's a possibility that you may not have the accurate prediction. But few degrees extrapolation is possible, but not beyond that. If you want an accurate prediction beyond that, then you should perform the experiment at those temperatures.
Sir? Yeah. Sir, if we are finding the shelf life on the basis of nutrition value, and if any product initially when it manufactured, then it gives suppose 100 milligram of nutrition, and after at the time of its expiry date, that means suppose after 6 months, it give, that means the over average they have shown like you will get 80 milligram per dose. So can we say that at the initial stage of that product, that means after manufacturing, say we can say like first month it will give us 100 milligram of, that means vitamins or kind of nutrition?
So the way industry does, because you have continuous degradation of vitamins, right? The amount, right? It is very hard to put on a label. The first month it will be this, second month it will be this, the third month it will be this, right? So what normally they do, that they have studied the degradation. So let's say initially they have 100, and they say, I'll give you example of orange juice. The pasteurized orange juice has a shelf life at refrigeration temperature of about 3 weeks. Okay, I don't know here how much, that's what it is there in some of the other countries. So now people do not buy orange juice just because how much vitamin C it is. The flavor and taste has to be there as well, right? So they see that it takes about 3 weeks to change the flavor, right, or change the taste. But they also want to now claim about the vitamin C, because some people may be interested in drinking orange juice because it contains significant amount of vitamin C. let's say they want to put on the label that it has a vitamin C content which is per serving is your daily recommended allowance, right? So let's say daily recommended allowance for vitamin C is, let's say, 500 milligrams, right? And they want to claim that if you have 1 glass of orange juice from this package, it can give you 100% of vitamin C, what you're supposed to have in a day. So they want to claim that it has 500 milligram. But now they also know that very first day, if they have 500 milligrams, within 3 weeks, it will come down from 500 to 400. But if they want to claim 500 milligram or 100% RDA on the label, so what they will do, they start with a 600 or 650. Okay, and they know that after 3 weeks, it will still have 500. So on the package, they will not claim that the first day you have 650 and then after 1 week it is 630 or 610 and then 2 weeks it is 550. They will just write a very simple claim that 1 glass of orange juice from this package will give you 100% of vitamin C what is needed in a day. So they have the more than initially what is written in there, but the last day of the shelf life, of that product, you will still have whatever is there on the label.
So just now we talking about that its degradation.
Correct?
So suppose we are storing the product at different packaging condition at different storages at different temperatures. Then how you can find out the K value at particular temperature? We supposed to take out the sample at particular time interval or what, sir?
Yeah. So let's say you are doing the experiment with orange juice, right? So an orange juice has initial amount of some vitamin C, and you store it at, let's say, refrigeration temperature, 4 degrees C. You store it for 3 weeks. Every second, third day, you take it out and see the level of degradation happening.
You just now told about that 3 week period. What should be the time interval? You should find out that K value from initial to up to unacceptable level of that nutrients, or any you can do for 10 days or 15 days.
No. In order to make any curve on a graph, you don't need 1 or 2 points. So if it is about 21 days of storage, maybe you should have 6-7 data point collected, and then once you have collected, then you would know at what rate it is the degradation is happening.
Yes, sir. That is what I am asking. Whether you go for K value in days of periods or K value in terms of up to our unacceptable level for that particular.
Well, when you do the lab experiment, you can do it for longer period of time, right? When you do the kinetics, you don't know whether initially it is 650 and exactly in 3 weeks it will come to 500, right? You would know that, right? So you do the experiment for 4 weeks, 5 weeks or 6 weeks and keep on monitoring. So you will have the data point for longer period of time and you fit your graph in that period, and then you would know at exactly what number of days you are reaching to the 500, your end point.
So can we have more than one shelf life of the same food product based on the critical concentration of its different composition?
Well, you could. It all depends upon you. For example, on that package, one company, let's say ITC, wants to claim that it has 100% of vitamin C in that juice based on the daily recommended allowances, right? And it has a 3 weeks of shelf life. So within 3 weeks, flavor is good, color is good, taste is good, but vitamin C comes from 650 to 500, right? There is a parallel, another company, they did the experiment, they say, hey, the juice is good, not 3 weeks, actually 4 weeks. People can still taste the good flavor, good taste, but then in 4 weeks, vitamin C is not now 500, it's actually 420. Well, if they want to claim 4 weeks of shelf life, they can put on the label that this 1 glass of orange juice from this package can give you at least 400 milligram of vitamin C. So it was the same process, same food, but the claim is different. They are claiming that it has 400 because in four weeks it is able to maintain 400. But other companies is claiming 500, and the 500 they are able to maintain for only 3 weeks. After 3 weeks, it's not 500. So if the labeling claim, whatever they have, if they change, and other parameters are not affecting from the consumer perspective, then yeah, the same product has actually 2 different shelf life.
But it has to be regulated, like.
Correct, of course, of course. Here we are assuming that the flavor and taste are being maintained for 3 weeks as well as 4 weeks.
Based on the critical composition of the different
That would be based on the sensory evaluation by consumer or whatever sensory panel they have. They said, yeah, 4 weeks it is maintaining the flavor profile.
But 2 different companies cannot claim 2 different shelf life for the same type of product they are introducing in the market.
Well, if sometimes processing condition could be different also, right? If you buy, let's say, biscuits, different companies are baking differently. Maybe they are incorporating preservatives, they are maintaining different moisture content or different water activity, they're using different packaging. Well, it's still their biscuits, but they can claim different shelf life.
So how we decide this critical concentration?
Critical concentration of what?
Any composition, like if you are conducting any experiment on any food component, like say we are taking a spice,
Correct.
spice powder, so we want to study the shelf life of any spice product.
Fine.
So on what basis we will study its shelf life, like what composition we should choose, of which we should know the critical concentration or the initial concentration, on the basis of which we, like there are several components, as you mentioned in your lecture, water activity can be, or moisture content can be one of the composition, or vitamin content can be one of the composition. So while conducting an experiment, on what composition should we focus more? Like if you take for example, if you are taking spice, so on what composition and what should be the parameter for selecting that composition on which our shelf life should be studied?
Okay. Are you able to follow the question? Who wants to answer this?
So I can.
Okay.
Because as far as spices is concerned, so Spice Board of India already declared this, suppose international market, if you want to export any product from India, in Spice Board of India has already fixed the certain parameters, such as its aflatoxin contents for any European countries or American countries, they already fixed. And FDA 2003 already published one risk, that pathogenic risk for particularly spices and herbs. Based on that report, we can already set the parameters for different spices. So we can consider that critical parameters as in our storage study, and based on that critical parameters, we can fix our shelf life of the product.
Okay. Anybody else wants to answer this question? You can look the same question many different ways. So for example, for certain food product, safety is the primary goal. You want to make sure that product is safe, right? And then once 2 different products are equally safe, then how do we compare? Based on the quality, right? And what is that quality? It depends upon that particular product. So let's say he has a spice. Before you sell a spice, you want to make sure that it's microbiologically free, or the load is whatever is specified by the regulatory agency, that you cannot have load more than that, that's going to be harmful, right? So that part you are achieving for sure, right? Now, once it's pathogen free and microbiologically free, then that particular spice people buy for which reason? Flavor, right? So that's your critical quality parameter or primary quality parameter, that you want to monitor flavor. Now, is flavor affected by what? it could be affected by the moisture content, right? If it is higher moisture, then it may suppress its flavor, because higher moisture may also germinate some or may induce some enzymatical changes. So all eventually is going to affect the flavor. So your goal would be to find out under the certain storage condition and package condition how long this flavor you are able to maintain. And then a time when you find that, so you should know whether how you are monitoring the flavor. Is it by sensory or using some GC, gas chromatography? So that's the instrumental method. So whatever method you pick and whatever limit you set, that at this flavor concentration, people are not going to like it. They will find that this is not acceptable. So that's your final concentration, right? So whatever quality attribute for which you are selling your product, that's what you want to monitor. People don't care color for that spice, then you don't monitor color. But people say, no, people also want to make sure that it has a good flavor, but that color also. Because if it has a flavor, but if it doesn't have that color, then people are going to reject. So then you want to monitor during your shelf life study that color as well. So you want to maintain flavor as well as color. And then based on that, you will identify the shelf life. And if these color and flavors are affected by, let's say, moisture absorption or moisture gain, then you want to look at how a different packaging affects the moisture gain, and that how this moisture gain affects the shelf life, or which is the flavor, how it affects the flavor and color. Make sense?
Sir, how will then act with respect to the new product development? That means suppose if we develop a new product that is not actually familiar with all kind of consumers. That means we are talking about the consumer preferences while selecting the shelf life modeling. Like suppose if we have a new product at the same time, and the consumers don't know about the product, then how we can, on the what basis of parameters we can model the shelf life kind of.
Good question. Who wants to answer this? Do you follow what the question is? Let's say Pizza Hut is selling a pizza. You know, there are few varieties of pizza they have. Now he comes up with totally new recipe for pizza, new toppings, new types of cheese, new type of sauce, right? Now he wants to find out the shelf life of that pizza, but he does not know what quality attribute he should consider. How he will go about that, right? Am I right? That's the question? Yeah. Okay, so how he will go about it?
So general market survey.
What would be that market survey?
Like sir, in 90s, when Nestle introduced Maggi to the Indian market, what they did that they started distributing this Maggi on free basis. Like they used to open a stall somewhere in the market, and then they used to prepare Maggi and then distribute it free to the consumers. And then they used to take their feedback, and depending on their feedback, they standardized or like they made some modifications, and they brought it to the taste of this the local people. So that way, means like by doing local survey, we can know the customer preferences on what attributes they are attracted towards a product, and based on those feedback or survey, product development can be proceeded.
That's correct.
That's the one way.
Yeah, that's correct. So anytime any company brings a new product which people have never seen, then they do this market survey. They say, do you like it? You say, yeah, it's very good. I really enjoy it. And then they would say, so what do you enjoy in this, really? Do you like, let's say it's pizza, you like a crispy crust? Or you like it's very cheesy? Or you like the toppings? Or the sauce is flavorful, right? So if it was a Maggi, what do you like? Do you like it's an instant, it cooks in 2 minutes? because I just don't have a time. I don't bother too much about flavor, but it really cooks 2 minutes. That's really very important for me. Or some people say, no, that's also fine, but the flavor which I see, that I really like it. So with that survey, they identify what is the quality attribute for which people appreciate that product.
So this is the only method. This is the only one method, or any other else we can say?
Sir, this is in case of industrial products, sir. What if we are preparing our product, new product in the laboratories?
Well, still, you're preparing laboratory with ultimate aim to sell it in the market. So one or other way.
Go to market and we can have all these parameters, sensory parameters. We should be having our judges for sensory evaluation. Based on those scores, we will be preparing some product. Then that product will be sent to the market for analysis.
So that's another way. Rather than directly going to the consumer, there are some people, like they mentioned, that sensory expert, right? Those sensory expert actually know that if you do any changes in the formulation or quality, people are going to notice. So rather than going hundreds of different consumer, these 3-4 people in a company, can you provide you similar guidance what you have the survey from 100 or 100 plus consumers. So that's another way. But it still is a feedback from people, because eventually these products are going to be consumed by people.
So just now you're talking about that, suppose the people expected the products with 6 months or whatever. And 6 month shelf life and all. In present study we are doing just preparing the product, and then we are just studying its degradation, K value, and based on that we are fixing the shelf life on mentioning pockets. But last few days we were talking about the NASA is targeted for the food products with shelf life having 5 years. Is it possible to fix the 5 years shelf life of the product? We can fix the degradation K value. Based on K value, we can adjust the composition of our product.
You can go this route also, but what would be the need for that? See, for example, NASA wants five years. Companies, they don't want 5 years. Then there is no need. Company thinks that they produce, because if the product is 5 years just lying around, then company will not be producing. Company wants that we produce, and it should be quickly consumed. Quickly means in the time frame they are able to distribute whatever their distribution chain is. If the distribution takes several months to go from Kashmir to Kanyakumari, then they want to have that time frame so that after distribution people still have sufficient time to consume. And that's the shelf life they are looking. You know, NASA has a different challenge, Army has a different challenge, a requirement, right? So you can always do that. And in fact, people for Army and NASA, they are doing that. Okay, because we need 5 years, how do we reformulate our product to get as high as possible, right? Because every effort would require expenses, right? But if there is a, consumer is not ready to pay for those expenses, our industry is not, then there's no need to.
Then is it possible, sir, to fix the first degradation, and then just at the time of product development in industrial level, you can fix that K and then come back to our composition?
How would you fix, tell me? How would you really fix? It's a goal is there to have as high as possible, right? The goal is there, intention is there, but without doing experiment and really by measuring, you will not know whether it is giving you that level of degradation or not. Yes, intention would be there that I want to develop a new kind of a biscuit which should give me about 2 years, and what kind of ingredient I can combine to have close to 2 years. Yes, that's the aim, but then you keep doing experiment until you reach there. Yeah, that's always possible, yeah.
And also it depends on the type of product, which type of product we are manufacturing, for whom we are manufacturing. It depends on that, sir. Actually, this shelf life, sir is talking about this Maggi. To whom we are targeting that product, that is very important. So those who are having fast lifestyle, they need faster foods, means fast foods. So they don't have sufficient time to cook in their homes. So we are developing those products for that group of consumers. It entirely depends on that basis.
Yeah, so that's what I said. You know, for some consumer, preparation in 2 minutes is more important than flavor. So you know that if it does not cook in 2 minutes, because that's the quality attribute of that noodles, that 2 minutes. So your formulation is taking if 3 minutes, then you go back and on your drawing board and modify the formulation or modify the process so that what final product you have, it cooks in 2 minutes.